So, water. It is wet.
Yep.
So, water is everywhere on the planet. Oceans, rivers, and lakes cover about 75% of Earth's surface. Water is essential to living organisms. 70 to 90% of the mass of a living organism is water. It just depends on what living organism it is. If it's like a jellyfish, you're probably looking at closer to 90% of it being water. Chemical reactions of biological processes take place in water-based solutions. Your blood has water in it. The air has water. Like, it's everywhere, people. It's a big part of the water cycle. The sun powers the water cycle. It drives the formation of clouds, which is called condensation. Then the clouds precipitate. Liquid water, or even, I guess, solid water, falls to the earth. And it can infiltrate the soil or run off into lakes, rivers, streams, oceans, where then it can evaporate back up into the atmosphere, creating clouds once again, and the cycle repeats continually. So, looking at the structure of water, we have two hydrogen atoms bonded to one oxygen. We've talked about partially positive and partially negatives before, correct? Yeah. So these symbols make sense to you? Yeah. Okay, so this should be a reminder that the oxygen atom is highly electronegative, meaning it makes the water, or that oxygen atom, partially negative. It's attracting the electrons in the molecule towards that oxygen atom. It makes the water molecules polar because we have the negative ends over here and the positives on the hydrogens. We have a bent structure due to two lone pairs of electrons on the oxygen atoms. Remember, lone pair of electrons kind of force the angle down. Those lone pairs need extra space. And then the bond angle right in here is 105 degrees, roughly. So, polar molecules have the ability to attract one another because of dipole-dipole forces. Remember, dipole-dipole forces is a fancy way of saying opposites attract. So that would be the positives attracting the negatives. Low electron density around the hydrogens cause them to be slightly positive, and that attracts them to the negatives of another oxygen from a different molecule. So this dashed line right here represents that dipole-dipole attraction. It is not a bond, and that's why it's dashed. A bond is represented by that solid line. This right here is what we call a hydrogen bond. Even though it's not technically a bond, it's an attraction. It is stronger than normal dipole-dipole forces. This is review, right? Do you remember hearing these words at least? Good. And if Studi says yes, and he slept through most of this chapter, so that's good. Ice is a bit of an anomaly because it is less dense than its liquid counterpart. Liquid water is a fluid. That means that we're constantly breaking and reforming those hydrogen bonds as the liquid molecules move over one another while it's being poured or transported. As water cools, molecular motion speeds up or slows down. Slows down, good. The molecular motion will slow. This causes molecules to move closer together, and that would mean the density should increase. However, for water, that is not true. When water molecules slow down, they move closer together to a point, but then they stop. So that means that solid water, aka ice, is actually less dense than its liquid counterpart. This is not a norm for all solids and liquids. Water is the one that breaks this rule. You know this because ice does what? Ice is frozen. You put ice cubes in a glass of water, what do? They float. Ice floats, and that is the observation or the indicator that it is less dense than the liquid. So this table shows you the different temperatures and then the densities of water. Notice that the temperatures are in degrees Celsius. So when we're at the 100 degrees Celsius before it vaporizes, your density is just under 1. And as you cool it down, what happens to the density? It increases. Okay? That's normal until you get to 4 degrees Celsius. Then after 4 degrees Celsius, at 0 degrees when it's still in the liquid state, the density drops to 0.9998. And then once it turns to the solid, the density is even less at 0.9168. So what temperature is water its most dense at? 4 degrees Celsius. This is why you have like foggy mornings when it's just above freezing, because that water vapor is so dense. It's at its densest point, so it will hang low in the atmosphere, aka at ground level. Other properties of water: it has a relatively low molar mass. Most molecular compounds of similar molar masses are gases at room temperatures. It has a high melting point, and it takes lots of energy to break apart those hydrogen bonds. And that means it also has a high boiling point. We've talked about surface tension before. This water has a high surface tension because of those hydrogen bonds. If you are ever asked a question like, why does water have this? Your best guess, if you have no clue, guess, because of the hydrogen bonds. Okay, that is pretty much your get out of jail free ticket when it comes to water. If you can explain about the hydrogen bonds and how the hydrogen bonds form because of the polarity of the molecules, you'll probably save yourself. Okay. Vapor pressure. It has a low vapor pressure, again, because of the strong hydrogen bonds. This means very few molecules are able to escape the liquid phase just as is. If you just have a bottle of water sitting on your desk, that's not going to evaporate in 50 minutes because it has a low vapor pressure. This results in low evaporation rates. This is a good thing because otherwise your larger bodies of water would evaporate away quickly. So this is good because it maintains water levels in large bodies of water. So like your lakes, your rivers, your streams, your oceans.